Black holes are one of the greatest scientific enigmas within our universes. And they might just be as cool as these sunglasses. Theorized in 1915 by Einstein and 1783 by John Mitchell, these celestial bodies were believed to have had such strong gravitational attraction that even light would not be able to escape. These cosmic bodies were made up of several unique scientific phenomena that gave them these powerful forces. First, on the outer region of the black hole, relativistic jets and an accretion disk surround the celestial body. A ring of heated gas and dust orbits the black hole at unprecedented speed, with some even passing through the event horizon, a point in which no light or matter can escape, thus feeding into the black hole. In turn, the black hole produces jets of radiation nearly at the speed of light. These gases that travel through the event horizon eventually reach the singularity, the center of the black hole that collapses this matter with near infinite density. Near the event horizon, a bright orange ring surrounds the black hole, and this is called the photon sphere, because it's an emission of photons from nearby relativistic jets. This is because the singularity distorts the motion of these photons, which are packets of light, in a relatively circular manner. That's why we see this bright orange ring here.
But how do other objects actually revolve and behave around black holes? Major astronomer and physicist Carl Schwarzschild considered this notion, developing the Schwarzschild geodesics equations, a set of differential equations that model the motion of objects and light rays around a non-rotating black hole. More specifically, we must look at this differential equation. 1/2 times d over dt squared plus v of r equals epsilon. Let's break this down, because this can look very intimidating at first. Starting with r, this is the radial distance between the object in orbit and the center of the black hole. When the object moves, r changes, and this is sort of the main variable that we are going to track with this equation. T here is time, more specifically, the proper time experience on the object's path through space. As the object moves through the curved space around a black hole, we're using t as a stopwatch to track time. Therefore, from what we know, d r over dt is the rate of change of r with respect to time, or the radial velocity. It represents how fast the object is moving relative to the black hole. This helps us understand how the radial distance r changes over time. The term 1/2 times d over dt squared as a whole represents the kinetic energy, something to keep in mind for later for sure. Moving on to our next term, v of r is the effective potential. I'll get more into that in the next slide, so just remember it. Finally, we have epsilon. This is the total energy of the object per unit of mass, and it is a conserved number. So, working back to the effective potential, rather than adding each individual force in the object separately, the effective potential packs them all together into a single function. It covers the pull of gravity inwards and the outward impact from angular momentum, which is the object's tendency to move away from the center because of its rotation. So this equation here is derived from the original differential equation that we were talking about, and it's not too important to know what all the terms and how this equation works. It's just important to understand what this is. And the way that I like to think about this is the potential energy of the object that we're looking at. So when we're observing the original differential equation with our new knowledge, we actually notice that the differential equation is structured very similarly to a conservation of energy equation, where the kinetic energy in the first term plus the potential energy in the second equals the total energy of the system. So now that we have a good understanding of the equation, let's see what it actually tells us. This graph here plots the effective potential, V of r, on the y-axis, with r, the radial distance, which is on the x-axis. Each colored curve represents a different object. So we talked about how the differential equation looks like conservation of energy. Kinetic energy plus potential energy equals total energy. We can use that. Picture drawing a flat horizontal line across the graph at some value, and this is going to be our total energy, epsilon. Wherever that line sits relative to the curve tells us what r does over time, or how the object moves radially. So if the line sits above the peak of the curve, the object has enough energy to keep moving outward forever, so it escapes from the black hole. If it is in the valley of the curve, r bounces back and forth between the two distances, and the object becomes trapped in an orbit. And then if the curve has no value at all, like the orange line at the bottom, there's no stable point for r to settle. The object sort of just falls into the black hole. So the differential equation isn't just a simple formula. It actually maps every possible way an object can move around a black hole, depending on its energy and how far away it starts from the black hole.
But finally then, how can we see this differential equation manifest within tangible applications of physics and real life, and why is that so important in the first place? With this differential equation, we're able to analyze and predict the curvature and behavior of objects or rays orbiting around black holes. With this, we physics scholars can help optimize pre-existing scientific principles such as relativity and gravity to help further understand their influence in space and time, especially regarding black holes. By better explaining these notions, we can apply our knowledge towards other orbiting bodies, such as planets like Mercury, for example, a body whose orbit didn't follow scientific predictions at the time. Today, we've used this differential equation to model orbits best through the Global Positioning System, or as we often dub it as GPS in our modern day-to-day. The Swarzchilds geodesic here helps optimize the straightest possible path within a curved spacetime, thus giving you the fastest and quickest way to get from point A to point B. But additionally, these geodesics can better explain how extremely strong forces of gravity can help affect surrounding objects given their position relative to the black hole. This means that you can see whether, say, light can escape at a given point, or how much faster or slower an object is depending on its position in its orbit. These analytics are especially important on humanity's journey to learning the ongoing mystery of black holes further, as these celestial bodies are still under great discovery and potential scrutiny. Look to the first black hole image humanity could capture from the Event Horizon Telescope collaborations right here. Scientists at the time had to utilize the geodesic equation to predict and help get the clearest image to try and visualize how light behaves at given intervals of the black hole. With that being said, discoveries such as these can help us broaden our understanding of the relationships of black holes and maybe someday how we ourselves can make use of them in our day-to-day lives. While we could see some sort of use of that to benefit us, we would ideally hope that no individual would have to fear of being sucked into the point of no return or the singularity. But even though we're at this point in which we're advancing, we would also wonder, how far can humanity progress without delving into the point of no return?